Ladies and gentlemen, today we are going to explore the concept of large number in statistics. This concept is fundamental to our understanding of how random variables behave when we take repeated measurements. To start, let us consider a simple example. Suppose we roll a fair six-sided die once. There are 6 possible outcomes, each with a probability of 1/6, since the die is fair and has 6 sides. Now, let us imagine rolling the die multiple times. What is the probability that we roll a 1 on at least one of the rolls? We could calculate the probability of rolling a 1 on each roll and then use the multiplication rule to find the probability of rolling a 1 on all the rolls. However, this calculation does not tell us the probability of rolling a 1 on at least one of the rolls. To find that probability, we need to use the concept of large number. The concept of large number states that when we take a large number of measurements of a random variable, the average value of those measurements will converge to the expected value of the random variable. In the case of our example, the random variable is the outcome of each roll of the die. The expected value of this random variable is the average of the possible outcomes, which is 1 plus 2 plus 3 plus 4 plus 5 plus 6/6 equals 3.5. This means that if we roll the die many times, the average of the outcomes should converge to 3.5. Let us see how this works in practice. If we roll the die 10 times, the probability of rolling a 1 on at least one of the rolls is approximately 51.5%. If we roll the die 100 times, the probability increases to approximately 99.4%. If we roll the die 1,000 times, the probability increases to approximately 99.998%. If we roll the die 10,000 times, the probability increases to approximately 99.99998%. This increase in probability occurs because as the number of rolls increases, the sample size increases. As the sample size increases, the sample mean becomes more and more representative of the population mean. The population mean, in this case, is the expected value of the random variable, which is 3.5. It is important to note that the concept of large number does not apply to all random variables. It applies only to random variables that have a well-defined expected value. For example, the concept of large number would not apply to the result of flipping a coin, since the expected value of the result of a coin flip is 0.5, which is not a possible outcome. The concept of large number is used extensively in statistical inference, which is the process of making inferences about a population based on a sample. For example, suppose we want to estimate the mean height of all students in a particular school. We could measure the height of every student in the school, but this is impractical. Instead, we could take a sample of students and use the sample mean to estimate the population mean. The larger the sample size, the more accurate the estimate is likely to be, thanks to the concept of large number. The concept of large number also plays a crucial role in many statistical tests and models. For example, the central limit theorem states that when we take a large number of independent samples from any population with a finite variance, the distribution of the sample means will be approximately normal. This is a powerful result, since it allows us to make inferences about the population mean based on the sample mean, even if the population distribution is not normal. In conclusion, the concept of large number is a fundamental concept in statistics. It states that when we take a large number of measurements of a random variable,